In this video, we're going to review what we've learned about atoms so far, and then set the stage for our next level of understanding about atoms, which is going to involve the electrons. We haven't talked much about them. We know they're negatively charged. We know they're somewhere in the outside of the atom, but where in particular are they, and how do they behave, is what we're going to look at in this unit. Here's our story so far. So far, we've discovered that everything is made of atoms, and so John Dalton imagined a little spherical, maybe bead kind of thing, like a BB, an indivisible atomic structure. And that's the simplest form of all matter, atoms. Then J.J. Thomson discovered that these atoms contain electrons, which are little negatively charged things scattered throughout the atom. He thought the electrons were in there in a positively charged mush that became the plum pudding model of the atom. But then Ernest Rutherford discovered that in the middle of here there has to be a fairly massive, positively charged item called the nucleus. And that nucleus, James Chadwick discovered, is made up of two even smaller particles yet, and some of these particles are positively charged, and that's what makes the nucleus positively charged. Those items are called protons, and then some of them have no charge at all, and they are called neutrons. If you have two atoms that have the same number of protons, those would be the same element. That's what defines an atom as a particular element. So for example, if my nucleus contained 3 protons, that would have to be lithium, which is atomic number 3. Any other atom with 3 protons would also be lithium. The number of neutrons in different isotopes of the same element can vary. So this atom has got 3 neutrons, but if I had a different atom that had 4 neutrons in it, that would also be lithium, just a different isotope of lithium. As scientists began asking themselves the question, where are the electrons in the atom, they started to notice that there was a connection between how light behaved and how atoms appeared to behave. And they started to look for explanations for that connection. To understand what the atoms are doing with light, or how light interacts with atoms, we have to first learn a little bit about what light is. What light really is an example of what's called electromagnetic radiation. Electromagnetic radiation travels through space as a wave, but it's not a wave that has a medium, like a string wave on a guitar string or a water wave in the ocean. It's not that kind of a wave. It's a wave that requires no medium at all. What's changing is something called a field. There's a change in a characteristic that's related to energy. I have a little demonstration that might help out. This little space here, I can drag positively charged particles in here, like a proton. I'm going to put one there. And I can put negatively charged particles in here, like an electron. I'll put one there. When I click on this field, you can see these little arrows, and the darker the arrow, the heavier the field. What this field represents is where would the force on a positively charged particle be if it were anywhere in this space. So right in this zone here, you'd see that a positively charged particle would be pushed away from this other positively charged particle. If I were closer here to the negatively charged particle, that positively charged particle would be pulled toward it. And you can see that those arrows sort of line themselves up in that way. By taking away the sensitivity, you can see that the arrows in general are pointing from the plus to the minus. You can see these streamlines sort of that go from one to the other. Now I'm going to take those arrows away, and I'm going to introduce an electron field sensor. This is really just a positively charged particle, and drop it in my field. Now it's got an arrow attached to it that shows the size of the field. As I move this around, you can see that the size grows and the direction changes as well, well, wherever it is. So I can influence the motion of the particle by the potential that's around it. Anytime I get close to the negative, the attraction grows and points toward the negative. Anytime I get towards the positive, the repulsion grows and points away from it. So the sizes of these fields can vary. I'll take my proton away and have only my negatively charged particle here. Watch what happens to the size of this field as I move this back and forth. Accelerating this particle changes the field. If I move it this way, I also see the field get bigger and smaller. So this field can change depending on the things that are around it. So if an electron is moving back and forth really rapidly, I see a change in both the direction and the size of the field. So what is a field? Well, a field is just like a region in space where a charged particle could respond. So if I were to drop an electron in this zone, it would move through the field towards the positively charged little gold sphere that we have here. This is an example of an electrical field. A magnetic field, you've probably experienced this firsthand. If you have a magnet and you move anything that responds to a magnet close to that magnet, you can feel it start to pull towards one pole or the other of the magnet. That's a field. That pull that you feel is the response of your object to a field. Well, it turns out whenever there's an electrical field, there's also a magnetic field. And what we're seeing here is two waves. The waves are really just changes in the size of one of those fields. You can see the arrows grow and then they shrink, grow and then they shrink. And they change direction as well. Perpendicular to the electrical field, which maybe we'll say is the red field, you see a blue magnetic field that grows and shrinks at the same phase exactly. Now you shouldn't get in the habit of thinking about electromagnetic radiation as having these sort of string wave-like properties, because they don't. But this gives us a model of what happens to the changes in field size as a wave of electromagnetic radiation goes through space. And the fact that wiggling around charged particles, like fast-moving electrons, could give rise to changes in field size gives you an idea of why the scientists were very interested in looking for the connections between light and the electrons that are in atoms. This chart here shows an electromagnetic spectrum, which is the spectrum that includes all the electromagnetic radiation, not only the part that we can see. The part that we can see, the visible light, you can see is a very small part of this spectrum, and it's kind of in the middle of the chart. If we move to the right on this chart, we see the wavelengths get shorter and shorter and shorter. Visible light is about 10 to the minus 6th meters, so that's about a millionth of a meter in wavelength. And the length of waves get shorter and shorter and shorter. They get smaller and smaller as we get towards the right. This includes radiation that we have probably heard of before, like X-rays, or maybe gamma rays, or ultraviolet radiation. We can't see that radiation, but it's the same sort of energy as light. It's just too blue for us to see, too short for us to see. Shorter wavelength radiation carries more energy. Some is too long for us to see, and that's what we see on the left-hand side of this chart. The redder it gets, the longer the waves. So off of the red end of the visible spectrum, we start to see the wavelengths get longer and longer, to the thousandth and the hundredth, and then to the meter, and then they start to get bigger and bigger, up to 1,000 meters long. Infrared light is light that's pretty close to visible, but we can't see it. And then there are microwaves, and then there are radio waves, a whole wide variety of these different bits of electromagnetic radiation that are not visible to us. In a future video, we're going to explore what this all has to do with the electrons in the atom and how the original scientists got a clue as to what it might all mean.